Okay, so it's good to see some more people today than yesterday. I know with the storm and everything, it was a little hard to get in for a lot of folks. I just wanted to make an announcement that I already made on Canvas, but just to tell the class that just in order to stay on schedule and to make sure that you have all the tools you need to complete homework 3, I wrapped up entropy, including osmotic pressure, in a recorded lecture video that I posted to the Canvas page. So if you go over to pages, it's linked right here as lecture 9.5 on more entropy and osmosis. And so I'd encourage you to watch that in order to be able to do the homework and in order to have a more full grasp of the course material. And in my announcement, I also outlined which sections of chapter 14 I expect you to know. So the first 2 we went through in class yesterday, and then the other 2, 14.3 and 14.7, are described in the recorded lecture. And so now we're moving on to chapter 15, which is all about oscillations. And so we're leaving thermodynamics behind. We're not going to continue to build anything else on those concepts. So the only reason you need to finish learning about them is for the homework and the final. But for now, we'll start oscillations, which actually will roll over and connect in a lot of ways to what we learn next about traveling waves, and then about optics and so on. So the tools that we're learning here with oscillations will be something that you'll see again as we develop over the next couple of weeks, the rest of the class. And this is our last major topic. So we had fluids, thermo, and now we're doing like oscillation and waves, which we'll see a lot of. Okay. So to start us off, we should think about what it means for something to oscillate. And another way of saying that something oscillates is to say that it undergoes periodic motion. Okay, and so periodic motion just means that instead of, if I get up and start walking to the right forever, that would not be periodic motion, because I'm never going to come back to a position that I once occupied. However, if I started walking to the right and then turned around and walked to the left, and then turned around and walked back to that same position that I went to on the right, and just did that forever at a constant pace, that would be an example of periodic motion. Now, that wouldn't necessarily be simple harmonic motion. We'll get in a minute to what that is in more detail. But periodic motion only requires that you're moving back and forth from one position to another in such a way that in a set amount of time, maybe 2 seconds, you'll have gone around your lap and returned back to your original position. And in another 2 seconds, you'll have done the same thing and be back at the same position again. And another couple seconds, you'll have done the same thing again. So in order for something to be truly periodic, we just assume that it will continue on forever, and that there's some set amount of time that we call the period that describes how long it will take for an object to return to that position. So you can see in this upper diagram that we have this period. And we can see here it's measured from the tip of one peak to the tip of the next peak. But we could just as easily take the time from this position where we're moving to the left through the origin to the next time that we're moving to the left through the origin. And we see that in both of those cases, the distance on the horizontal axis separating them is the same quantity, capital T. And similarly, at this leftmost point, we could also see that the time it takes to return to that position is this capital T. So capital T is the period, and it has units of seconds in metric system. But you can see that there's a difference between these two plots. So the one on the top is describing some motion where you're moving at a constant velocity from a position -a on the left to a position +a on the right. And then in an instant, so at this top point here, you instantaneously turn around and start moving the other direction again at a constant velocity, but opposite to your previous motion. And then down here, when you get to the leftmost point, you again turn around and start moving back to the right instantaneously. And so these sharp points, we call them cusps in mathematics, are something that you should always be suspicious of if someone shows you a graph like this and says that it describes the world. Because a sharp point like this means that at that point, you have an infinite acceleration. Because at that point, if you have taken a calculus course, you can't define a slope. You can't define a derivative. Because when you have a point, there are lots of lines that can touch that point without touching any other points on the graph. And all of those would potentially be some slope at that point. And so we just say that it's undefined. And the reason that's important is that when you have a position versus time graph, the slope tells you how fast you're traveling. So at the instant that we turn around, temporarily our speed is undefined if it's some pointy bit like this. And so students will often, including myself, back when I was a student learning this for the first time, will often think that this upper graph is the more natural graph, but this is actually unphysical, at least if you take it to be exactly true. You can have plots of position versus time that look similar to this with very sharp points, but if you zoom in, you'll see that they're rounded. And that tells you that the object was actually able to move like this. It actually had a well-defined velocity and an acceleration that wasn't infinite. And so it turns out that the more natural, the more physical way to have periodic motion is to have something like a sine or a cosine plot. And one way to see this is that a sinusoid, which is the name we give that sort of encompasses sines and cosines. So a sinusoid is smooth over its whole shape. There are no sharp points where the velocity would be undefined. And in addition, we'll see that it actually is something that we can get purely mathematically when you have a situation with a so-called linear restoring force. So if you think back to Hooke's law, where we had the force on a mass due to a spring is negative kx, so negative some constant called the spring constant, combined with the distance from whatever position the spring likes to be in, so the distance from the equilibrium. We see that the farther we pull that spring, the larger the force is. And it turns out that situations like this are really, really common. One way of thinking about it is that if you know what a Taylor expansion is, if you take a Taylor expansion of any arbitrary force, you're always going to have a linear term that'll tend to dominate. And so as a result, almost every system that has a complex force relationship exhibits some sort of oscillatory behavior due to a linear restoring force. And we're gonna dig into the details of the forces more later. But I just want to give you some reasoning, some intuition behind why we see these sinusoids all over the place when we start talking about oscillators. So one reason to say is that it's just natural to have a smoothly varying curve in a position plot such that you have a continuous and smoothly varying velocity and continuous and smoothly varying acceleration. But another way of seeing it is that mathematically, if you have a linear restoring force, it forces you into having a sinusoid as the solution. It's the only way that you can solve for a system like that. And so even though not many forces are exactly linear restoring forces, there are lots of things that are approximately like that. And we'll see some examples, one of which that's really important for chemistry is that molecular bonds actually act like tiny springs. We mentioned that when we were finding the heat capacity of a solid to be 3 times R, that that 3 comes from 6/2, so 3 degrees of motion in kinetic energy and 3 degrees of spring potential energy. And so those bonds exhibit a springiness, and you can actually make atoms wiggle back and forth, which affects what kind of radiation they emit, and is something that's measurable. And we can thus measure the bond strength of atoms by looking at the rate at which they oscillate, which is a very useful tool for analytic chemists. And you also see this type of motion if you have just something like a ball rolling in a bowl here. So if you drop the ball and let it roll back and forth, this acts almost identically to a pendulum, which is something we'll cover in more detail. And so yet again, we see a smoothly varying velocity as we go up the hill. It slows down, comes to rest, and then starts building speed the other direction. And so that would be a sinusoidal position versus time graph. So if it's been a while since you've seen these position versus time graphs in 3A, it might be a good thing to review them, just because we're going to be thinking about them in quite a bit of detail as we go through this section. Basically what you should know is that these positive values of position are telling you that your object is to the right of some origin, and these negative values are telling you that your object is to the left of an origin. And when the plot is sloped downwards, that's telling you that you're moving to the left, while as here where the plot is sloped upwards, that tells you that you're moving to the right. So those are the main features that you should be aware of. And if you have a point like this that's at a minimum or a maximum, then for a brief moment, your velocity is zero in such a place. And if you've taken calculus, you would just say that the tangent line has a slope of zero at that point. And so the slope of the tangent line is telling you the velocity for a position versus time plot. Okay, so that's those are some of the basics of oscillation. But like I said, everything I just described, we're going to develop in more detail. But hopefully this gives you a bit of an overview. Okay, so if we put a mass on a spring, and we use an air track here, which is basically like if you've ever played with an air hockey table where the puck is kind of elevated by jets of air, it serves to make friction negligible. So it's a very low friction environment. So if you have such a system where you just only have to think about the force due to the spring, you can ignore friction, then we get some oscillatory behavior that is exactly described by a sinusoid, a sine or a cosine. And so this is what we mean when we say simple harmonic motion. So simple harmonic motion, which we'll often abbreviate as SHM, or sometimes you'll see it abbreviated as a simple harmonic oscillator, SHO. Those mean the same thing, effectively. So a system that's in simple harmonic motion is one that's oscillating in such a way that the position versus time graph is a sinusoid. And as we'll see, the distinction between sine and cosine gets very blurry here, because sine and cosine are really the same graph, just shifted on the x-axis. And so in any oscillatory system, we can define the period, which was just, the period is just the amount of time it takes to make one cycle. So time per cycle. And we can also define the frequency, which is just the opposite of that. It's the number of cycles per time. And so frequency has a weird unit, which is known as the hertz. And so 1 hertz is just 1 cycle per second. So that means that the object, let's say that it started at the center, it would go to the right, all the way to the left, and then back to its original starting place. So the confusing thing about these sorts of systems is that in order to get, so if this is where we started, you can see that here we're moving to the right. We're going to pass through the 0 point again, moving to the left, but we haven't actually made a full oscillation until we're in the same position with the same velocity. So that's a really important distinction, that the period is referring to the amount of time that it takes to go from some position with some direction of velocity back to that same position with the same direction of velocity. Okay, So if you start at the center moving to the right, you're going to move all the way to the right, and then you're going to pass back through the center moving to the left, and then get all the way to the left, and then come back to the center. Now you're moving to the right. Now it's been one period. So play around with that in your head if it seems confusing. But it's an important distinction that just because you're back at the same position doesn't mean you've actually made a full oscillation yet. You have to also be moving in the same direction. But once you've done that, we call that a cycle. And so if you're oscillating at 50 hertz, what that means is that every second you make 50 of those cycles. So that would be, you know, with your hand, that's a very high frequency. But for some systems, that's a very low frequency. For example, we're going to talk about sound waves in a lot more detail later, but the human ear can hear frequencies between 20 hertz and 20 kilohertz roughly. So the lower limit most people can hear, but the upper limit is really determined by age and some of the properties related to the size and sensitivity of your ear canal. And so an experiment that I think they still do in the 3B lab is have you measure the upper frequency range of your hearing. And I know mine is like 15 kilohertz or something, so I guess I'm getting a little old. But anyways, hertz are a weird unit though, because technically when you write the unit's components, you just get 1/seconds. So cycles isn't really a metric unit. It's just something that tells us it's like a fraction. So it's like the fraction being how many times over how many cycles. And so in that way, it's very similar to angular measurements. So when we talk about degrees and radians later, you'll see that we often do include them in our units, even though if you're being very pedantic and you're, you know, a lover of the metric system, you would say those aren't really metric units and that we don't need to write them. But it's often helpful to do so. And similarly here with hertz, it's often more helpful to write frequencies in terms of hertz than in terms of 1/seconds, even though both are correct. Okay, so before we move on, any questions about simple harmonic motion and frequency and period? Do those concepts feel reasonable? Okay. So I'm going to do a couple of trig interludes today that aren't in the book, but that I think are important to have in the slides in case you want to come back and review. So on the left, we've got our old friend, the unit circle. So you will have to use your calculator in this class for trig related quantities, which is something I put in the syllabus. But it's good to know some sort of principal values of the various trig functions. And basically what it comes down to is if you can remember your 45-45-90 triangle and your 30-60-90 triangle, that's all that I really want you to, you know, you're not even going to be required to know that. You can always use your calculator in this course, but it's good to know. It'll save yourself some trouble if you remember those two triangles. And so then, you know, if we're trying to find, so if this is a 30-degree angle and we remember that our 30-60-90 triangle is x root 3, and 2x, then we can quickly find that the sine of 30 degrees is 1/2, and that the cosine of 30 degrees is root 3/2. We won't really have to deal with the tangent much in this section, so just focus your energy on sine and cosine. But what I want you to see here is that, so this is looking at 30 degrees. We can also take, in this triangle, the 60-degree angle as the one that we're interested in. So sine of 60 degrees would be root 3/2. And cosine of 60 degrees would be 1/2. So you can see that there's a relationship between these angles. And I wanted to talk some more about that relationship because we're going to see it in this section when we get to talking about phase. And so effectively the cosine curve starts at a position that's far away from the equilibrium in a positive direction, if we're interpreting this as like a mass on a spring or a pendulum. Whereas the sine graph starts at a point at the equilibrium, so at the origin, but it has some velocity, right? The sine graph has some velocity, whereas the cosine graph starts stationary. So a cosine plot as an oscillating system tells you that what you've done is you've taken your spring and your mass, it's sitting where it's in equilibrium, you've stretched it out and you let it go. That's a cosine. Okay, so when you stretch it out in the positive direction, that's getting it to this top of the curve, this green dot here, and you let it go without giving it any extra velocity. That's conveying that the slope there is 0. And then it's going to oscillate back and forth. The sine graph is like if you leave the mass at its equilibrium position, but you come in and you flick it. You give it some velocity. And again, we're giving velocity in the rightward direction, the positive direction. And that's why the slope is upward at that position on the sine graph. And so then once you flick it, it's going to move to the right, and then it's going to start oscillating. So you can see that how this graph has been shifted, right? We can think about shifting functions to the right or the left. So depending on how the function is shifted, that tells us something about how we started the system. Okay. You know, we could also imagine pulling the mass a little bit and then also giving it a flick. And that would be a more general curve that's neither a sine nor a cosine. It would be some shifted, something like, you know, cosine of x plus phi. But you can see that if we allow that phi to be minus pi over 2, that would give us sine. And that for sine, if we have a phi, so some extra angle of pi over 2, that would get us back to cosine. So sine and cosine are just the shifted versions of each other. And I just put these relationships up here in case you find them useful while you're doing the homeworks, both this one and the next one. And so you should also have a rough idea of when each of these are positive and negative. So sine is going to be you know, positive from 0 to 180 and negative from 180 to 360. Whereas cosine is positive kind of around 0. So from negative pi over 2 to pi over 2, and is negative from pi over 2 to 3 pi over 2, or however you want to break that up. In addition to working with degrees, which I guess is what I've been using so far, it's important that we develop your comfortability with radians, which are actually in this section going to be much more useful than degrees, even though you're maybe less comfortable with radians. And you know, it's really just a unit conversion. So every angle in degrees, if you just multiply it by pi over 180, that's our conversion. And you'll get a number in radians. It might be a nice fraction of pi, or it might be some messy decimal, either way. But the angle in radians has a really nice property, which is that if you take a circle and you have an angle of 1 radian, then that's the point at which this arc length has a length of 1 radius, if this is the radius of the circle. So 1 radian tells you that the distance you've traveled around a circle is equal to whatever the distance that the radius is at that in that system. And as a result, a lot of the formulas we'll develop in this class which might involve moving back and forth between physical distances and angular distances, will be more easily written down in terms of things that involve radians. So what I would encourage you to do is learn how on your calculator to switch between radian mode and degree mode. This is part of your homework. Or if you're not wanting to do that, maybe it's a lot of trouble, just commit to memory this conversion, 180 degrees per pi radians. And anytime you're working in the unit different than what your calculator is set in, make sure to convert before you evaluate your trig function. And a good way to check is to use the sine of 1/2, or sine of 30 degrees. So if you type in sine of 30 to your calculator, If you get 1/2, then you're in degree mode. And if you get some messy decimal stuff, then you're in radian mode. I don't even know what sine of half a radian is, to be honest, but it's not going to be a nice 1/2. So that's a way to check if you don't have much familiarity with your calculator menu. Okay, so we're going to have another trig interlude later where we talk about the inverse sine and cosine functions. But for now, are there any questions about what I expect you to know and be able to do with the standard sine and cosine plots and their functions? Okay. Sorry if that was all too much of a review, but I thought it would be nice to include in the slides. Okay, so then without proof here, but in relation to what we were just talking about, we can write down simple harmonic motion in the form of an equation, like this equation on the left, or alternatively, the one on the right. So these are both equivalent. The only difference is that on the left, we've used the period, and on the right, we've used the formula that F is just 1/t, and we've instead substituted the frequency. So you can use either one depending on what's convenient for you in the moment. And we'll even talk about another equation later on that just describes the exact same thing, but with different variables. And so just to give you, another rundown of everything in this equation. So this A is the amplitude, and this is this maximum position that your plot is extended to. Or so if you pull a mass on a spring outward and don't give it any extra velocity, then that's the farthest position that it will get from its equilibrium. So it'll then oscillate back and forth, but it will never get farther than that A point. And one way of seeing that mathematically is that sine and cosine, they can only give you outputs between -1 and 1. So you're never going to get something bigger than whatever is out front of your sine and cosine, which is what we call the amplitude. Then this capital T, this is the period. So this is how long it takes to make one cycle, one oscillation. And then your T here is your time that you're interested in. So this is some arbitrary time. And if you plug in some number, so for example, you plug in 2 seconds, then when you evaluate A cosine 2πt over period, you'll get the position of the mass at that time of 2 seconds. So it's a very nice function that just tells you where you're at a given time. Hopefully that's pretty straightforward. And the 2π has to be there because in this way of writing it, we're thinking about the angles in terms of radians. So the 2π in this formula, anytime you see pi's in these sines and cosines, that's telling you that you're working in radians. If you wanted to do this in degrees, you would just have A cosine 360 degrees times T over big T. And so the ratio of little t over big T, that's just getting you what fraction of a period have you traveled through. And if we know that at one period you've traveled through an angle of 2π or 360, then just by multiplying the fraction of your cycle that you've gone through by that one cycle's worth of angle, you get the proper argument for your trig function. And so then on the right, we have an example where we have a cosine graph for position. So you can see they actually write it for you right here. So this is what it looks like if you have a x of t that's A cosine 2π ft. And you see that they plot the period and the amplitude here just for your visual pleasure. And in addition, we are given the velocity curve. And you can see here that the slope at this point in the position curve is negative. And so the value at that point in the velocity curve is also negative. And that continues to be true. So you can see it continues to be negative until this point. And this point is where the slope is 0. So the velocity value is 0. And the really nice thing that you start to notice when you look at the derivatives of these functions is that, they're sines and cosines. So their derivatives are also sines and cosines. And that's one of the reasons that simple harmonic motion is more physical, more natural than that sharp sort of triangle graph we saw earlier, is that every derivative of a sine or a cosine will always give you another sine or cosine. And since sines and cosines have a nice smoothly varying continuous functional form that's consistent with, physical laws of motion, that means that so too do all of their derivatives, their velocity, acceleration, jerk, everything else. Okay, and so they give us here the velocity graph, and they put it in terms of this V max. So down here we have this V max value. And we'll see in a moment what that Vmax value is. We can talk about it in terms of the amplitude and the frequency of the position curve. But it's important to notice that the Vmax just acts as an amplitude, and the minus sign in front of all of this just tells you that you start off going downward instead of like you would in a normal sine graph where you would start off moving upward. But you notice that it has the same frequency or the same period because the velocity change is just related to the position change. We can think about that in terms of force or in terms of energy. So like I said, there's a nice relationship between the amplitude and frequency of the position graph and what's effectively the amplitude of the velocity graph. So this V max. So V max is basically, it's sort of similar to the amplitude, but for the velocity graph. And it has this nice formula, 2 pi f times a. If you're used to calculus, you may notice that when we take the derivative of a cosine 2 pi ft, the 2 pi f comes out front, right? That's the product rule, or sorry, the chain rule. And so as a result, the factor out front is now a times this 2 pi f, and that's exactly what Vmax is. And importantly, this 2 pi is telling you that something about the radians, the use of radians, is really important when we're thinking about how to get the right value for Vmax. If we had used 360 degrees instead, and we tried to do 360 times F times A, we wouldn't get a number that represented the meters per second velocity. We would get the velocity in some weird composite units. And that's an artifact of the way that radians, since they're telling you how far around the circle you've traveled in terms of meters, they're just a much more natural unit for going in between these physical measurements like meters and meters per second and angular measurements. So just watch out for that. As we'll see, it'll be more important later. So we have a little question here. So if an object moves with simple harmonic motion, if the amplitude and period are both doubled, the object's maximum speed is, so what happens here? So we have twice as much amplitude and twice as much period. What happens to Vmax? Exactly, it doesn't change. So we could just say this, our initial Vmax is 1 Vmax and our final Vmax is also 1 Vmax. So those two effects cancel out. And one way of seeing that is that, we're moving to a farther position. So we've stretched our spring out more, but something about the system is causing it to oscillate more slowly. It takes longer to move. So those two contributions balance out. The fact that we've pulled it farther generally would mean that it had more force, so it would move faster. But the fact that the period is longer tells us something about our system has changed. Something about the springiness has changed, as we'll see later. And so as a result, the whole thing moves more slowly, and these two effects cancel. So we get the same maximum velocity. Now the velocity at any given time, we would have to plug into this formula to find. So once you know what Vmax is, it's just 2 pi Fa. Then you can write that our V of t is just 2 pi Fa with a minus sign out front times sine of 2 pi Ft. So that would be our full function to describe the velocity at any given time. We would give you these formulas. We don't expect you to know how to differentiate in this class, but you can see that if you do have some basic calculus experience, they're really easy to get, at least once you know one of them, I guess. So I'll pause here. Are there any questions about maximum velocity or any of the terms we've been describing? Okay, very good. Hopefully that means that this is all eminently understandable. Okay, so we have an example here. So we have an air track glider, which, like I said, just is a way of telling you that this is a low friction environment. So this little bit just means that we can ignore friction. Is attached to a spring. So that's a good hint that we're going to have simple harmonic motion. And it's pulled 20 centimeters to the right and released. So this thing here is going to be our amplitude. It makes 15 oscillations in 10 seconds. And so the first, all of these questions, when you're given these questions for an oscillating system, what I tend to do is, unless the question is something very simple, just ignore all the questions they're asking and just get our x of t function. Because once you have that, you can answer all their questions very easily. Everything about the system, all the information that describes it is stored in this function x of t. So once you write that down, you kind of know everything. It's just a matter of pulling out the pieces that they're asking about. So if we want to get our x of t, we can see that we've pulled this out 20 centimeters and released it. So this is going to be a cosine plot, right? Because cosine starts at its amplitude. So at time 0, cosine is at a position 1. And so if we multiply by a, then this a cosine is at a position of a at time 0. And that's exactly mimicking what the actual glider is doing. And so our a, like I said, is just how far we've pulled this. So this is 20 centimeters. And then our frequency is the only other thing we need to find. And it also happens to be related to the first question they're asking here. And so this is just a number of cycles per second. So this is 15 cycles per 10 seconds, which is just 1.5 hertz. So you can see how we use the unit hertz here to talk about frequency. We could just as well say 1.5 inverse seconds. It just doesn't have the same ring to it though. And so if we're interested, we can also get the period, which is just the inverse of this. So 2/3 seconds. And then our V max, as we saw here, is just 2 pi F times A. And so if we're okay of units of centimeters per second, then we can just plug things in here. So 2 pi times 1.5 times 20. So I'll just grab my calculator really quick here. And I get 1.88 meters per second. And then finally, they want to know what are the position and velocity at 0.8 seconds. So this is where we can actually use our formulas. So our x of t is 0.2 meters times cosine of 2 pi times 1.5 hertz times t. And so we can plug in 0.8 seconds for t, and we can get our x of 0.8. And when I do that, I get 6.25 centimeters or 0.0625 meters. And similarly, our v of t, which we wrote down at the bottom right here, is just negative v max times sine of 2 pi ft. So we plug in our v max of 1.88, we plug in our frequency of 1.5 hertz, and we evaluate it at the time of 0.8 seconds. And I get negative 1.79 meters per second. So this would be one of our answers. This is one, and I think they asked for the period. This is one. So this is a pretty typical example of the type of problem you'll see on the homework, and that you'll see, maybe in a more elaborate form on a quiz or a final, where you're being asked basically to find x of t and then use it to do something productive. So we'll talk in a moment about the inverse problem, which is much more annoying. So if I ask you at what time is the mass at a position of 10 centimeters, that's a much more annoying problem because it's an oscillating system. So there are an infinite number of times where this mass will be at a position of 10 centimeters. And so, of course, those times will be related to each other by, some factors of 2 pi. But we have to be careful when we're evaluating them, because, the types of solutions, there are two types available. There is the type where we're moving to the right and the type where we're moving to the left for any given point. Unless you're thinking about that point where we turn around at the amplitude. And so we'll talk some more in detail about how you work with those sorts of systems later. So moving on to the next section in the book, it's important that we think about circular motion and simple harmonic motion as being related. And when we do this, we find that something like an angular velocity is responsible for the frequency that we observe in our simple harmonic motion. So they've got a couple of examples here, and this is actually something that you can see at home very easily. I know these look like elaborate setups, but you actually all probably have a turntable-ish thing that you have access to, which is a microwave. So a microwave is a great example where you have a rotating circle at the bottom. You can put an object like your mug on top of it, and you can look at the shadow or just look at the position of the mug only along the x-axis, and it will follow some sinusoidal motion. So as it goes back and forth, its velocity will change in such a way that it's exactly described by something like a sine or a cosine, which is really marvelous. And it's a result of the way, as we saw with the unit circle, that we can draw triangles within a circle, like this one right here. And then the x component of that triangle, which tells you the x position of the object moving in a circle, is just related to, in this case, the cosine of the angle. Or if we were looking at it from the other side, the y component would be related to the sine of the angle. So a sinusoid describes one component of the position of an object moving in a circle. And so an object moving in a circle at a constant angular velocity will, in one dimension, have exactly the same type of position graph as you see for an object that's on a spring oscillating back and forth. So that's what this picture is trying to show you on the left here, that this object on a spring, if we pulled it back just the right amount, basically the radius of the circle, and let these things go at the same time, that they would, the shadow of the ball would exactly match the position of the mass on the spring for, if we spin it at the right speed. Obviously we have to set this up carefully, but the shapes of the functions are the same. That's the important thing. And so when we do this, we can think about how for this angle phi, the x position is just a cosine phi. And if we're moving this circle around at a constant angular velocity, that we could instead write this as a cosine omega t, right? If you're moving at a constant angular velocity, then we can just write omega is phi over t, and we can rearrange that to say that phi is omega times t. And so as a result, the values that we get here will be, the function that we get is just, some scaled argument inside the cosine, which is very similar to what we had back here, except you can see that instead of 2 pi f, we have this omega. So we're actually going to define for our spring system, so for any simple harmonic motion, omega as just 2 pi f. And we actually give this a name because it's something that, all that it does is saves us writing 2 pi everywhere. But physicists are very lazy when it comes to things like writing. So we'll see this over and over again, and it's called the angular frequency. And all that the angular frequency is doing is it's, instead of talking about cycles per second, now we're talking about radians per second. So a cycle is just an angle. A cycle is just one revolution, so 2 pi radians. And so by multiplying f by 2 pi, we're just converting, so f has units of cycles per second, and 2 pi is our conversion between radians and cycles. So we can just cancel the cycles and now have something like a frequency, but with units of radians per second. And like I said, the whole reason we define this is so that we get something that's even more analogous to the circular motion. So in circular motion, that omega is the angular velocity. Here it's the angular frequency for a mass on a spring, but it also just mostly saves us from writing 2 pi everywhere. But it will be important for you to know this formula. I mean, it'll be on your formula sheet, but it's important that you know that it exists because you will be expected to, convert back and forth. It's often easier in a system to figure out what the frequency or the period is. Because if I tell you, like in this sample problem, if I tell you that something makes 15 oscillations in 10 seconds, that immediately tells you the frequency. That immediately tells you the frequency is 1.5 hertz. All we have to do is divide. But then once we do that, we have to convert. We have to multiply by 2 pi to get the angular frequency. So often the angular frequency is the thing that you want to work with when you're actually doing the math, because it saves you from writing. But the frequency f is what you want to have when you're trying to convert a physical system into the math, because that f is the thing that's more easily observable. Okay, so lots of words there, and we're coming up on our break, but are there any questions before we take a bit to stretch and talk? Okay, so then go ahead and stretch and talk and everything else, and we'll reconvene in a minute here. Okay, so hopefully that was a good break to get you back in the mood for some physics. And so just to write out in a bit more detail what we were describing a minute ago, we see that circular motion and simple harmonic motion are mathematically equivalent. And if we define this omega, which for circular motion is the angular velocity, and for simple harmonic motion is the angular frequency, but it's effectively representing the same thing in both cases. So we can say that it has units of radians per second and is equivalent to 2 pi times the frequency, or alternatively 2 pi over the period. Then we can convert our a cosine 2 pi ft into just an a cosine omega t. So much simpler. And like I mentioned, your microwave is a good place to play around and observe this phenomenon. And okay, so far we've talked about the amplitude and the frequency or period components of this equation, but now we have to start thinking about in a little bit more depth what we were doing in the last example. So in the last example, we had stretched out a mass on a spring and let it go. And I just argued that that should be a cosine graph. Maybe that sounded, a bit like I'm pulling this out of a hat. But the more that you get some experience with these sorts of situations, the more you'll be able to do that yourself. That if you've pulled something to the right, that's a cosine graph. If you pulled it to the left, that's a negative cosine graph. If you flicked it to the right, that's a sine graph. If you flicked it to the left, that's a negative sine graph. But what happens if it's some combination? If you pull it and flick it, right? If you give it some more complex initial conditions. And so that's something that we do want you to be able to handle. And that's where we come into the study of phases. So I know this is a lot of math on the page at once, but let's just focus on the top left, that top line here. And you see that all that we've changed is we've added this phi naught, this extra angle, and this is known as a phase. So a phase, let's take a minute, ignore all the trig stuff, put it on pause, and let's just think back to algebra class. So if you had the function y equals x squared, we could plot that and it looked something like this, just a normal parabola. But alternatively, we could have the function y equals x minus 2 squared. And so what would that function look like? Can anyone tell me? Yeah. Shifted 2 to the right. So 1, 2. So this is our new lowest point. And we have a parabola like this. I know my drawing is not perfect, but so all that we've done by subtracting 2 inside the argument of a function, so everywhere there's an x, we put a x minus 2, we shift that function to the right by 2. So subtraction shifts to the right, addition shifts to the left. And so that's what this phase is doing. The phase in these simple harmonic motion functions is just shifting our sine or cosine to the right or to the left. So if we go back to, well, let's just look at this plot. If we go back to our trig interlude, you can see here's cosine, here's sine. So if we shift cosine by 90 degrees or pi over 2 radians to the right, it would look like the sine graph. And in fact, that's what this trig identity is, right? It's all coming together now. So here we have a cosine plot with a phase of negative pi over 2. So that phase is, since it's negative, it's shifting our whole curve to the right. And when we do that, the cosine starts to look like sine. Alternatively, we could take our sine curve and shift it to the left. So that's a positive phase, and that'll make something that looks like cosine. So you can see we can easily go back and forth between sine and cosine by using these phases of pi over 2, plus or minus pi over 2. But in this section, on initial conditions, we'll think about general phases. So what happens if you have a phase of pi over 3 or 8 pi over 7, anything, any arbitrary number. Sorry, one moment here. I need a drink of water. And if you're familiar with calculus, then you can derive this yourself. But if not, it's written here that the velocity function stays almost the same. It just has that same phase in the argument, right? When you take a derivative, something that's a constant inside a function, the product rule ignores it. Or sorry, the not the product rule, like the chain rule yet again, ignores it. And so it only just remains inside the argument of the trig function. So Vmax isn't affected by the addition of a phase. It's just shifting our whole function to the right or to the left. And so we give some examples here, and this is a great diagram from the book, although I know there's a lot going on. But let's look at that leftmost column first. So you can see here, we have a phase, phi naught, of pi over 3. And we have to be careful about what we mean by that. So in this case, and let me see how the book refers to things, you see that we've shifted the function. So if we had started with cosine, we had started with cosine, that at 0 has its position at the amplitude, and we shift it to the left by pi over 3, then we get the function cosine omega t plus pi over 3. And so that's how we get this phase is pi over 3 radians. And that's represented by this position curve. You can see that our initial position is not at the amplitude, but it also does have some velocity. It has some negative velocity, some negative slope here. And we can contrast that with a phase of negative pi over 3, which is where we've shifted this cosine plot to the right by pi over 3. So you can see here that that amplitude has been pushed to a more positive time. So this whole function has been shifted to the right. And so this is represented by cosine omega t minus pi over 3. Both of these, I guess, should have an amplitude out front as well, but that doesn't affect the shape of the sinusoid itself. And then finally, we have the case of pi radians. So if the phase is pi radians, you can see that we actually start at a negative amplitude. And so we could just naively write this as cosine omega t plus pi, but we see that this is just actually equivalent to a negative a cosine omega t. So if you have a phase that's like a nice number, like a multiple of pi over 2, basically, or pi, you'll often just get like negative sine or cosine or something of that nature. So watch out for things that can simplify your life by absorbing that phase into creating a negative sign or into turning one trig function into the other trig function. And you can see that when we shift the position plot, the amplitude doesn't change, just sort of the left-right motion of the graph. And very similarly for the velocity curves on the bottom here, the Vmax doesn't change and the frequency doesn't change, just the, where is that plot at time 0? So, these points here, where is the plot at time 0? That's what's really changed in between them. And that's why we talk about phase oftentimes in terms of what we call the initial conditions. So the initial conditions are how we start our system, how we give it some initial energy, maybe potential energy, maybe kinetic energy, that leads to the oscillatory motion that we're interested in. And so we can practice a little bit with this example, but this is going to be a little bit more in depth maybe than the last example, because now we have to start thinking about how we're actually going to calculate a phase. So we have an object on a spring that oscillates with a period of 0.8 seconds. So they just tell us the period for free. and an amplitude of 10 centimeters. So I'll just be consistent in this problem and make that 0.1 meters. And they tell us the initial conditions. So I like to sometimes write like initial conditions I see here. So at time 0, the position is at 5 centimeters to the left. So this is negative 0.05 meters. And it's moving to the left. So our velocity at time 0 is negative. And what they want us to find is what are the position and the direction of motion at 2 seconds. And so again, no matter what sort of question you're given for these oscillatory system problems, generally what you want to do is you just want to find x of t and v of t. And those, once you get those functions, you know everything. And you know, those functions are really related to each other by a derivative. So you actually only need one of them and you know everything. But once you get both, it's really the sky's the limit. And so what we can do is we can write out our initial condition, and we can use that to solve for the phase. Okay, so we know that our x of t is going to look something like a cosine omega t plus phi. You can also write these as a sine omega t plus phi. I would encourage you when you're finding phase to use cosine, right? They're equivalent. We could use either one because they're just, you know, if you use sine instead of cosine, it'll just change the value of phi. It'll, you know, be changed by plus or minus pi over 2. But cosine has a nice property, which is that it's called an even function. So it looks the same to the right of the y-axis as it does to the left of the y-axis. And as a result, we can solve for the multiple solutions with inverse cosine more easily. So I'll walk you through what that means in a minute. But basically, it boils down to if you're using a phase angle in a problem that's not just a nice like pi over 2 or pi, I would encourage you to write down the trig function in terms of cosine. It's just going to make your life easier in the long run. So anyways, we know that our system is going to follow this sort of behavior, and we can plug in everything that we know. So x of t is 0.1 cosine. So omega is just 2 pi over the period. So this is just going to be some number, so 7.85 radians per second. 7.85 t plus phi. So the only thing we don't know is this phase angle. And in order to get it, we want to use this information that we call the initial condition, which is where the particle is at time 0 and what direction it's moving in. So we evaluate, we say x of 0, they tell us that this is equal to negative 0.05. And we know that the general equation is that at any time, x of t is 0.1 cosine 7.85 t. Oop, got a 5 there. 0.85 t plus phi. And so now we have what are known as trig equations. We have a trig equation. We're going to have to solve for something, and our t is 0. So this we can just cancel out. So now we're solving for the argument of a trig function. So we have cosine of phi is just negative 1/2, right? If we divide by 0.1 on both sides. So does everyone see how I got cosine of the phase is equal to negative 1/2? So far, so good. So I'm plugging in x of 0, which the problem tells us is 5 centimeters to the left, so negative 0.05. And then I'm saying at time 0, that 7.85 t bit goes away. It's just 0. So all we're left with is cosine of phi is negative 1/2. And so now what we have to do is we take the inverse cosine of both sides. So we're going to have phi on the left side, and we're going to have the inverse cosine of negative 1/2 on the right side. And so this is where you have to be careful. So first of all, this is a good place to check what mode your calculator is in. But when you do an inverse cosine, you'll always get a positive number. So inverse cosine of anything, so of any, in this case, shouldn't write phi, of x, it'll always be something between 0 and pi. So this is why it's more useful to use cosine instead of sine. So sine, it'll be between negative pi over 2 and pi over 2 when you take the inverse. So that'll just make your life a bit more annoying. But basically, for cosine, when we plug this into our calculator, it'll give us this first value, which will be some positive number between 0 and pi if we're in radians mode. And so if we plug in cosine of negative 1/2 into our calculator, it'll give us that phi is 2 pi over 3 radians. But that's not the end of the story. So this is where drawing a graph is very helpful. So sorry, that's a really crappy cosine graph, but you can see that 2 pi over 3 is somewhere down here. So this is on the x-axis, 2 pi over 3. So we're looking at this position where the graph is 1/2. And you can see that at that point, the velocity is to the right. We're moving to the right. But that in general, there are two types of solutions. There are rightward solutions and leftward solutions. Sorry. At this point, we have a negative slope. So here we're moving to the left. Here we're moving to the right. So sorry about that. But you can see that there are these two types of solutions. There are ones basically before the minimum and ones after the minimum. And there will be, an infinite number of those solutions that are all related by factors of 2 pi, because this is a periodic function. But this is where cosine is really handy, because you can see that however much we have to move to the right, in this case, 2 pi over 3, to get to the first solution, which for this problem is one that is before the minimum. If we move the same amount in the negative direction, we'll get to the other type of solution, the one to the right. So the other type of solution here is negative 2 pi over 3 radians. And to either of these, we can add a multiple of 2 pi. So, 2 pi, 4 pi, 6 pi, 8 pi, or negative 2 pi. We can add any multiple of 2 pi, and we'll get another valid solution. So these are all of the possible phases just based on solving the inverse cosine of negative 1/2. So if you, go to Wolfram Alpha or something like that, that can handle these sorts of equations, and you ask it, what is the inverse cosine of negative 1/2? It'll give you this whole thing in the circle as an output. All of those infinite angles are solutions to cosine of negative 1/2, and we can split those infinite angles into two categories. They're the ones related to 2 pi over 3, where the object's moving to the left. So this is moving to the left, has a negative slope. And there are the ones that are related to negative 2 pi over 3, where the object's moving to the right, where the graph has a positive slope. But in the problem, they give us a little bit of detail. They tell us that at time 0, that the object is moving to the left. So what we can then say is that our phase is just positive 2 pi over 3. So, come back and rewatch this part of the lecture if this is confusing, or there are lots of tutorials online as well. But in effect, when we're solving for the phase based on some arbitrary initial conditions, we have to carefully work our way through plugging in a t equals 0, solving the inverse trig problem, and remembering that we have two types of solutions. And so for cosine, that's really easy to do. We just have ones that are whatever our calculator tells us plus 2 pi in, And then we have ones that are negative, whatever our calculator tells us, time plus 2 pi n, right? Our calculator gives us this value here. And then you have to think about when you're, the easiest way to do this is to look at the graph for that problem. You have to think about what kind of solution is it here. And in this case, the one that actually describes our motion is based on the positive phase. So are there any questions about that? Yes. So you add 2 pi n to both sides, just because if let me give you an example. If I know that the sine of pi over 6 is 1/2, then I could just as well say, or let's do this in degrees because it's maybe easier. If I know the sine of 30 is 1/2, then I could also add 360 to that, and I could say the sine of 390 is also 1/2. I could add 360 to that again and say the sine of whatever that angle is 1/2. So I can add, I can go around the unit circle and get back to where I started by adding multiples of 360 degrees or 2 pi radians, and I'll get the same output. So for both of these cases, I can add an arbitrary multiple of 2 pi. Sorry, those n's aren't the same here. The n in both of these cases is just an arbitrary integer. So +1, +2, +3, or -1, -2, or 0. And so that's just a way to get all of the possible solutions. When we write down the phase, we tend to just write down the smallest one. So usually we set n to 0, because if they're all equivalent, why write bigger numbers, basically? But if on an exam, if you gave me 2 pi over 3 plus 2 pi as the answer here as for the phase, I would say that's correct. It's the same. There's nothing wrong with that. It just makes your life a little harder when you go to write I don't know what that would be, 8 pi over 3 over and over again instead of 2 pi over 3. It's an arbitrary difference. Does that help? Yeah. Okay, good. Very good question. Any other questions while we're here? Okay, excellent. And so I guess I should say then, so once we get this phase, we can plug it in up here. So I can just erase this quickly and sneak in a 2 pi over 3. And then we just plug in 2 seconds, and that'll tell us our position at 2 seconds. And then similarly, we'll have this velocity function here. We can plug in 2 seconds. The phase will still be 2 pi over 3. Omega will still be the same. And we can solve our system that way. And our Vmax, remember, would be A times omega. Right, Vmax is, I know we did this a little bit ago, Vmax is 2 pi f times A. We could more easily write this as A times omega. Maybe that helps you remember the formula. Okay, so that was a long example that I guess I didn't even fully finish, but hopefully the most important part of that, finding the phase, is something that makes more sense now. And so before we leave, one more little check your understanding question. So the figure below shows 4 oscillators at time t equals 0. Which one has the phase constant positive pi over 4 radians? So let's take a moment to look at these. So so just assume that these are all, they're at this 71% of the amplitude. So, you could go into your calculator and look at what, cosine of 71 over 100 is. You'll get something related to pi over 4. And so it's just a matter of thinking of which of these actually represents pi over 4 as the correct phase. Okay, so what we need to do is we would have our cosine of pi over 4. So at time t equals 0, so our x of 0, remember that the omega t becomes 0 if t is 0. So this is what our function we want it to look like. And so cosine of pi over 4, this is going to be some positive number that's less than 1. And so as a result, we can narrow it down to these two, okay, because our x position, just plugging in a cosine of the phase is positive. And now we have to look at, our v of 0. We can go back and see that that's negative v max sine omega t phi naught. So if we plug in 0 for t, then this is negative v max sine of pi over 4. And our v max is positive, it's just a times omega. And so our sine of pi over 4, since this is in the first quadrant, that would also be positive. You can plug it into your calculator as well. And so overall, for a phase of positive pi over 4, we expect a negative velocity. So we narrow it down to the bottommost plot. So this one would be our phase of pi over 4. So you can see that, depending on what the phase is in a system, that fully describes the so-called initial conditions. So it has to relate to both the initial position and the initial velocity, or the direction at least of the velocity, to tell apart between the two possible types of solution. So thanks for bearing with me on all this math heavy stuff today. We're going to dive back into it tomorrow and continue talking about oscillations.